All right, welcome back. So some people, I think, prefer to watch it on YouTube later, and some people prefer to come. So as you are here, you might as well take advantage of it and ask a lot of questions and so on. So I sort of prefer a smaller interactive group than left like 100 people. That's not the case here, fortunately. But then it gets harder, right? Because you feel like I don't want to disturb all these other people. So now feel free. So you might have noticed we posted the results of the midterm. We are still debating like the details, like what to do about the feedback type of stuff. Overall, I think it was pretty good. But let me work a little bit more on how to get back to you, what to fix, like to meet with the TAs and so on. Have you seen it yet, the results? Okay. Yes, somebody was asking if there's going to be another project. There will be another project. We will get there. It will be on some linear differential equations. I guess I will get there slowly. Okay. So last time we started talking about linear differential equations and how, because that's another very important application of eigenvalues and eigenvectors. Okay. And what we came to was that the solution of linear differential equation or system of linear differential equations is closely related to the concept of matrix exponential. So maybe I can start by explaining again what's the idea of OD, of a system of ODEs, of system of ordinary differential equations. I think before I did it for the 1D case, but actually I realized I like it. It makes a little bit more sense in the 2D case. So let's take a look at the vector case of ODEs. It's also more practical because the 1D is like a little bit too simple. So what does it mean if you have like a system of two linear ordinary differential equations? Well, that means that we are searching a function. We are looking for the unknown is a function. Let me call it v rho, which is a function from R to R2. Okay. So what do I mean by that? Well, or it could also be a function from like 0, 1, from an interval 0, 1 to R2. Okay, but this doesn't matter so much. What matters is it goes to R2, which means it has two components, right? So you could write it, so it's gonna be a function, so there's gonna be some parameter t, which can be either an R or from 0 to 1. And it has two components. This component, let's call it Vx and Vy t, or both of them would be just regular functions. Vx and Vy would be just single one-dimensional functions, okay? And in the case of linear differential equations, what we are asking from this function v, which we are solving for, is that v at t derivative equals a v t. So I guess I should explain what is the derivative. It's sort of obvious. So if I differentiate this, that means that I differentiate each of the functions separately, right, per component. Yes, that's obvious. So the derivative is another vector function of exactly the same signature from R to R2. Okay, so this would be a 2 by 1 thing. A here is a 2 by 2 matrix. And v, of course, is again a 2 by 1 function. Okay, so the important thing is that, remember that the v we are looking for is a function. So therefore, is it sharp enough? A little bit better. So the v prime is also a function, right? The derivative of a function is another function. So then you can differentiate it again and get second derivative and so on. And we will actually get there in a little bit when we'll be talking about higher order differential equations, okay? But let's talk a little bit more about this example. So let's give this some geometric intuition. So I guess, sorry, the point I was trying to make here is that the VTs are functions, so the t is varying, the parameter, those are functions, but the a is constant, okay? That's important. So it's a system of linear differential equations with constant coefficients, which are encoded in this matrix A, okay? So let's give this some geometric intuition. So what this function essentially means, if we took a function from interval 0, 1 to R2, how would you interpret it or imagine it? That's also why I like it better than the 1D case, because this already is practical. So basically this, if the function v is smooth, then this will be a smooth curve, right? If I look at my plane, then this basically is like a parameter domain, okay? And what the v function traces, it traces some curve, for example, like this, right? So for t equals 0, this would be my v at 0, okay? This will here, right here, would be my v at 1. Somewhere here would be v at 0.5, and so on, right? So if the v happens to be smooth, I'm tracing exactly a smooth curve, okay? If I allowed the real axis here, then it would be the same, that the curve would be infinite, okay? What you often see in physics, you would have a domain which goes from 0 to infinity, which means it starts somewhere and then goes on and on and on and never stops, at least conceptually, okay? I guess this is what would be studied in differential geometry of curves, but the basics are very simple. So is that clear, that this basically is a curve? Okay. If it wasn't smooth, then the curve could have some sort of like sharp features there. But let's not complicate things. Like that's always in mathematics, you have like assumptions and so on. Let's assume everything is nice and smooth. So under this assumption that everything is nice and smooth, what's the interpretation of the derivative of v? That's a very useful thing to get intuition for. Well, I guess we can first write a definition, right? So the derivative of v at some point t would be the limit for h going to 0 of v t plus h minus vt divided by h, right? So that's just the definition. It trivially splits into the individual derivatives, right? Because these guys are just 2D vectors. This is just a scalar, so it trivially splits into the two independent components, okay? Is that something pretty clear? So what is the interpretation of the derivative? For example, here at the v 0.5. So if I have the derivative of v at 0.5 for this particular function, what is it? Intuitively. You know that? Or can you figure it out from the definition? It's similar to like standard derivative, right? Here on the 2D case, where it actually makes a little bit more sense. You remember I was a little bit uncomfortable talking about the 1D case when I was talking about like the analogy of an ocean current, because it wasn't exactly that in 1D, but in 2D it will be exactly that. So yeah, any ideas what is the derivative there on the picture? The v, or you can also write it like d over dt, right? There's many notations for that. It's the same thing. Well, think about it. Or is it too trivial that you don't even? I'm not quite sure. Looking at your faces, I think it's probably not. So, well, the idea. Okay, look at this. What does it mean? This means that I move myself in the parameter domain by a small h. Okay. So if small h is like this, for example, and then I subtract these 2 points, so I get a vector like this, and I divide by the h. Okay, normalize that. So this basically means that that's the idea of a derivative, right? So the derivative of v at 0.5 is nothing but the velocity of the point at time 0.5. So if you imagine there is like a point, or like imagine there's like a 2D car driving from 0 to 1 on this line, okay? So it's moving. It starts here and it goes with some speed until it arrives here, okay? And the derivative tells you exactly what is the instantaneous velocity of the car at point 0.5 or any t, right? So in particular, it's important to realize that the derivative is tangent to the curve. I guess that's the very basics of differential geometry. Okay, and it's very easy to understand from this intuition, right? If the idea is that you move infinitely small in the parameter domain, and you see how did it change. Okay. All right, so that's basically what we are. That's explanation of the ODE in 2D. So that's a system of two linear differential equations for a specific matrix. Okay. So what does it mean to solve the ODE? So what we are given is the A. Okay. Somebody gives us the A, and I think the last time I thought we will look at this particular A. So I'm gonna solve this in a minute. So for example, this A is going to be sort of interesting. But let's first think, what does it mean for arbitrary A? Okay, what does the right-hand side of the ODE tell us? Well, it tells us for every point in the plane, it tells us what the instantaneous velocity of the point, if it ever will be traveling through the point, will be, okay, of our imaginary car or something, okay? So for this point, for every point, so if I guess my point is x and y, what I'm gonna do, I'm gonna apply A to x, y, and I will get a vector, and that's my instantaneous velocity at that point. If my car or whatever I imagine is sort of tracing the curve, ever will reach that point, okay? Doesn't have to, because to be able to write down a solution, I have to provide a specific solution. I have to write down an initial condition, okay? I have to say, okay, I have to start somewhere, okay? For example, at time 0, I start here, okay? So this, I say that my V0 is given. That's my information. Then you can imagine that this, basically at any point I can imagine, any point in this plane, I am given the direction, and then the task is to find the trajectory which traces these directions, essentially. It's the analogy as we talked before. If you imagine that the vector field is like an ocean current, and you drop a particle into the ocean current, and the solution of the ODE is the curve the particle traces as it's being advected in the ocean current. And in 2D, I actually like this much better, because in 2D, these velocities are exactly right. In 1D, it wasn't really the case. It was like a little bit uncomfortable even drawing these arrows, right? Because in 1D, we only had like one derivative. So these arrows are like technically not correct, because they are just like 1D scalars. You assume you always do like step of 1 on the x-axis. But in 2D, that's exactly what it means to solve an ODE, okay? Trace a particle through a velocity field, and in the case of linear ODE, the velocity field is described just by a constant matrix, okay? So the idea is that you are looking at a point, okay? With the point, you can associate a vector. That's your vector x, y. You multiply the vector with matrix A, and that gives you another vector, and that's the velocity at that point. Okay? Sorry, did I explain this enough? I think so. All right, so let's take a look. Let's see if I didn't miss anything. Yeah, that's good. So let's take a look at an example. Let's take a look at the example where A is this matrix. Okay. So I guess you can start by thinking, what does this matrix actually do, or how does the vector field defined by this matrix actually look like? Okay. What do you think? So let's take a look at it. So I'm saying that my matrix A is 0, -1, 1, 0. Okay. So how does the vector field look like? So if I apply the matrix A to some x and y, what do I get back? I get -y and x. Okay. So if I'm to draw this, so for example, if I pick a point here, what vector will I get here? So this point will have some, this is my x-axis, of course, right? This is my y-axis. So this would be my x-coordinate. This would be my y-coordinate, right? What I'm gonna do, I am gonna take the -y coordinate and make it x. So that goes here. And then I'm gonna take my x-coordinate and make it y, okay? So it happens that if I draw the arrow here, sort of like, it's like a velocity from there. So it's just this vector rotated by 90 degrees counterclockwise. Okay. If you remember the general form of a rotation, then you immediately see that this is actually a rotation by 90 degrees. Clockwise. No, counterclockwise. CCW, counterclockwise. Right? So if I take another point here, so this would be my corresponding vector, and the velocity here would be like this. Okay. So for any point I pick, I can pick like another point here, for example, right? Like here I get a velocity which is just this. So the length of the vector is the same, right? This is a rotation matrix after all, so the length of the vector does not get changed. So this is a particularly simple but already interesting velocity field, right? What does it give you? Some sort of swirl pattern, right? Do you see that? Can you imagine it? Or if I pick a point like this, then I will get a velocity that points in this direction. If I put a point like this, I get a velocity like this, and so on, right? If I went far away, then I will get a velocity like this. So what do you think the solution should be if I drop the point into some initial location? You're gonna actually compute it, so we're gonna apply exactly what we discussed the last time, because what we discussed the last time, the solution, so if I start somewhere, let's say I start at some point P, okay, which P would be some xn or px and py, px and py, so let's say I start somewhere, or you can call it v0 or whatever you want to call it, right? And from what we discussed before, we know how to find the solution, right, mathematically, using eigenvectors and eigenvalues. So in general, the solution is just given by exponential of the matrix times t. T is the parameter that will trace the curve of the solution, and y0 is the initial condition. Do you have a guess what it's going to do intuitively? Or maybe we can just compute it, and then we can connect it to intuition. Okay. So do you understand what we need to do to find the solution of this ODE? We need to the hard part is to compute the exponential of the matrix. Okay. So and not just the matrix, we need to compute exponential of AT. Okay. So I'm gonna multiply this by t, where t is my free parameter. That's the parameter of the curve, the parameter that will trace the solution. Okay. And how do I compute the exponential of the matrix? Well, clearly the scalar parameter t doesn't really matter there, but what matters is the eigendecomposition of A. Okay, so in other words, I think that's what we discussed. Or let's just look at it again. So this is basically the matrix exponential is just generalization of the Taylor series or the power series for the exponential of a real number. So for a real number would be the same. I guess I have just like lowercase a here. And we can just plug in a matrix, right? And if we have a diagonalizable matrix, which that turns out to be the case, then we can use the eigendecomposition. And we know that the higher powers, they basically don't have any other effect but raising the eigenvalues to some power. Okay, so if I take a squared in the eigendecomposition, it means just v lambda squared v inverse. Okay. And that means that the entire exponential essentially reduces to just v, which v is the matrix of eigenvectors, exponential of the matrix of eigenvalues. That's a diagonal matrix. Okay, so that's something very simple because you just exponentiate the diagonal and the inverse of the matrix of eigenvectors. Okay, so that's exactly what we need to do to solve this problem. Okay, so let's do it. So we need to find eigenvalues and eigenvectors of this matrix. So if I write down the characteristic polynomial, then I will get this determinant, right? So minus lambda here. I assume you already know the drill, how to find a characteristic polynomial. So that's this, right? And you immediately see, and we need to set this to 0. So this implies that the eigenvalues are, we will not get confused by the complex numbers, that they are I and minus I, right? Because both I and minus I, when I square them, I get -1. So add it to 1, that gives me 0. So that's the root of this characteristic polynomial. Okay. So that's the case of a matrix that is diagonalizable, but we need to go to a complex domain. And actually, that's actually my entire point in this example, that going to complex domain is actually the natural thing to do here. You will see that once I write down the solution. Or can you already see what the solution is going to be? So, okay, so wait for it. So I have the eigenvalues, that's clear. And now I need to compute the eigenvectors, okay? So I guess I'm just gonna tell you what the eigenvectors are. It's 1 and I mean, you know how to compute it, except that you need to compute it in complex domain, which is a little bit annoying because they are complex numbers. So the eigenvectors are, oh, you know what, let me put the minus here, and 1 and I. So again, you should not be surprised that they come out as complex conjugates, right? Both the eigenvalues and the eigenvectors are complex conjugates of each other, right? Because the theory guarantees that has to be the case, okay? So if I'm going to write the matrix of eigenvectors to diagonalize the matrix, so it will be 1 and minus I, that's V1, and 1 and I, that's the other one. And if I'm to compute V inverse, what I will get is 1/2 of 1, 1, I, and minus I. Okay, I'm not going to do all the computations, otherwise this would take forever, but you can trust me, that's what it is. It's very easy to verify it in MATLAB, for example. I mean, to verify it is actually is easy, right? Because you just need to do you just work it out that this is the inverse. So it's 1, 1. You can just do it like immediately, right? It's immediately there. The only tricky part is the minus I squared, which is 1. Another 1 times 1/2, so that's 1 on the diagonal. So that is the correct inverse. Okay. By the way, this is a special case of in the complex domain. We often don't need to just transpose the matrix. This is the conjugate transpose. So in complex domain, we often don't use just transposition, but conjugate transposition. That happens to be exactly the case here. But never mind. That's not the point. Either way, this is the inverse. Okay. So to write the exponential of TA. Now we know how to do that, right? So what I need to do is to, I think I have this one, is to take the matrix V and then write the exponential of the eigenvalues, okay, times t. So in this case, it would be e to it, 0, 0, and e to minus it, okay, where I is the complex unit and t is our parameter, and V inverse, okay. So they are complex, we have to deal with it, but again, this is actually the point here, okay? Well, let's take a look, what did we get? So we can plug in back the V and V inverse, okay? So let's just work out the multiplication, I guess, one by one, that makes most sense. So let me plug in the V. And this is EIT 0, 0, E minus IT, and here is V inverse. So how much is gonna be the product? So let's do that. So here I will get EIT, right? That's easy. Here I'll get E minus IT, and here I'll get minus EI minus IEIT. It's funny. And here I can't. Okay, so I just multiply these two matrices together. Okay, nothing that special going on there. And I think I forgot the 1/2 somewhere. No, 1/2 is in V inverse, so that's fine. Okay, so I just multiplied it. So let's multiply it with the V inverse too. So let me plug in. So this is the 1/2 from V inverse, and this is 1, 1, I, and minus I. So let's multiply this together. Gets a little more funny, but not for long. So this will be EIT plus E minus IT, right? That's this dot product. Then here what I have E IEIT minus IE minus IT, right? And here what we'll get is, I'll sum the second row plus IE minus. These minuses are quite important there, so have I got it right? And here I will have minus I squared, which is 1, right? So that will be just EIT. And is again minus I squared, which is again 1, which is plus E2 minus IT. Okay? Did I do it right? Did you check on me? So, it looks like a big mess so far, but there is a way to organize this mess into something quite beautiful. So you know, you remember Euler's formula for complex numbers, right? That's the key thing here. So e to it is nothing but the cosine of t plus I sine t, right? By the way, we would get this again directly just from the power series for exponential. If you plug in complex numbers, it still works, and we would get exactly the Euler's formula. Okay. So that's the guy we have here. So if I write it for e2 minus it, well, that's similar, right? Then I have cosine of t minus I sine t, right? And if let me just write them, I have also these guys multiplied by I. So if I just write it here for convenience so that I can simplify it easily, then this will be, of course, just this, right? And here is minus sine t. And if I have I e to minus it, then I will get I cosine of t, and here is minus I squared, so that's plus sine t. This is sine, of course. Okay. What I'm going to do now, I'm going to take these expressions and plug them in here, and I will see what do I get. So this will be 1/2 of what? So let's look at it. So this is E. Are you following me? So this is e to it plus e minus it. So I'm summing these first two terms. Okay. So what I see, well, the I sine t's, they cancel, right? And I'm left here just with 2 cosine of t. Cool, right? Here is EIT minus, so that's this guy, minus this one. Okay. Well, if I do minus, then the I cosine t cancels amazingly, and I will get minus 2 sine t here. Okay. What happens here? Similar thing, right? Here I have minus this plus this. So that gives me 2 sine t this time. Okay. And here I have just the same thing as here, EIT plus E minus IT. So that's again just 2 cosines of t. Okay, so this is nothing but cosine t, sine t, sine t, and cosine t, and here is minus. So what matrix is this? About angle t, right? And if you think about it, this makes perfect sense, right? Because all that's saying, so now I can actually write explicitly the solution, right? So my v at time t is the exponential of ta times wherever I started, v0, okay? But I just derived that this is nothing but the rotation by angle t of v0, okay? That's the solution. So that means that if I start here, what I'm gonna get is just rotating just a circle going around. So the parameter t here is tracing the circle like that. And that exactly makes sense, right? Because if you compute the velocity vector here anywhere, then the velocity vector is just a vector tangent to the circle. If I compute it here, I get another tangent. So that's exactly what you would expect from this velocity field. So the solution of this linear differential equation is a rotation matrix. So I think this is quite cool. So this is also sometimes called that this is an example of an anti-symmetric matrix. But anti-symmetric matrix means that if I do the transposition, look what happens if I do the transposition of this. I will get 0, 1, minus 1, 0, right? Which is exactly minus A, okay? So these matrices are called anti-symmetric. It's like the counterpart of symmetric matrices. So symmetric matrices would not change anything if I transpose them. If I transpose the anti-symmetric matrices, well, they change their sign. And that's all that changes, okay? So what we have just seen here is that anti-symmetric matrices are generators of rotations. Or you can also look at them as essentially linearized rotations. Linearized in the sense that they give you the instantaneous velocity of a rotational motion, okay? So that's exactly what this does. If I have a point somewhere, what the matrix AX does, or AP, where my point is P, it tells me the instantaneous velocity of the rotational motion. And if I solve the corresponding system of ODEs, you see that the exponential reduces exactly to a rotation matrix. So I think this is quite cool. How would this look like in 3D? Let's take a look at the 3D case. So was this clear? I would like you to. Yep. Any questions? So if so, we can look at the 3D case. So what do you think will be 3 by 3 anti-symmetric matrices? So the funny thing about 1D anti-symmetric matrices, so you can, like, 2D anti-symmetric matrices, on the diagonal they must have zeros, right? Because if I transpose it and I want to get minus A, well, the only number which is equal to its minus is 0, right? So on the diagonal there must be zeros. So 2D anti-symmetric matrix is only 1 degree of freedom, right? So all 2D anti-symmetric matrices look like this: 0, 0, A, minus A, right? Or I could write minus A here and A here. It doesn't matter, because that would be the same family of matrices. So 3D anti-symmetric matrices, they look similarly. So they look like this. Let me parameterize it, and I will explain in a little bit why do I denote the non-zero elements exactly this way. Minus B, A, 0. So that's a general form of a 3D anti-symmetric matrix, and you can see it has 3 degrees of freedom, okay? So the key thing here, so the ABC would be just real numbers. And the key thing here is that they are basically mirrored. So there are zeros on the diagonal, right? That's the first thing to realize, that must be the case. And that these numbers are just mirrored, right? So the one that's here, if I mirror it along the diagonal, I just get minus the number, okay? So that's why only 3 degrees of freedom. And do you know what a 3D anti-symmetric matrix does to a vector? So I mean, if I have some point P, which is coordinates x, y, z. So what do I get? So let me call this A again. And if I do AP, do you know what this does? So let's take a look. So if this is 0 minus CB, C0 minus A minus B, A 0. You might be wondering why I just didn't put A, B, C here, but it will be clear in a second. Have you seen this before? Do you know what this will do? There is a very well-known term for that. You can think about it. That's basically a way to generalize this from 2D to 3D, right? The same idea. So we are again looking at instantaneous velocity of rotation motion. Okay. So that's the geometric picture, and the algebraic picture, we can just compute what this is, right? So that's obviously just minus Cy. Just do matrix vector product Bz, Cx minus Az, and it's minus Bx plus Ya or Ay, whatever. And do you know what this is? This is nothing but, or does this ring a bell? So the A, B, and C, you can look at this as a vector, right? Because the matrix only has 3 parameters, A, B, and C. Okay, so I can write this as a vector a, b, and c. And this x, y, z I can also write as a vector x, y, z. Okay. And do you know what operation produces exactly this? Exactly, that's exactly the cross product, right? If you remember the rule for a cross product, you know that the first term will be bz minus cy. That's exactly what we have here. The second one will be minus az plus cx, the determinant thing. And the last one will be ay minus bx, so that's exactly what we have here, okay? And that's exactly what makes sense, okay? Because the ABC, again, that's an axis of rotation, or if I'm to be more precise, let me denote it as a vector u, a, b, c, okay? So the normalized u, that would be exactly the direction of an axis of rotation. And then the cross product with the axis of rotation tells me the instantaneous velocity. If I'm rotating about, now I'm in 3D, so it's sort of difficult to draw, but you can imagine that you have an axis in 3D, and you have like a rigid body or something that's rotating about that axis. And if I give you a point with coordinates x, y, z, the cross product is how you compute the instantaneous velocity of a point on a rigid body rotating about this axis. Oh, so this would be the direction of the axis, and of course the norm, the square root of the length of the vector, that would be the speed, okay? So if you scale the axis up, you're actually making the rotations faster, the velocity field is more pronounced. If you scale it down, it's getting smaller and smaller. I guess the extreme is you scale it by 0, then there is no motion at all. That's like a degenerate case, okay? So that's basically this idea lifted to 3D, right? So what happened in 2D, we only have one axis of rotation, effectively, right? This one, the z-axis, there's just one. In 3D, we have infinitely many possible axes of rotation, right? The z would still be there, right? What would be, the 2D one would be that if we would set the ABC to be 0, 0, 1, right? If I do that, then my A reduces to 0, minus 1, 1, 0, 0, 0, 0, 0, 0. So we are indeed back to the 2D case, right? But this can handle any 3D rotation axis with any velocity. And the cool thing is, just like in the 2D case, you can proceed and compute the exponential of this matrix. So compute the exponential of TA. And guess what you will get? Now the guess will be a safe bet. So let's assume that the A was computed from a unit length vector. Or okay, let me be a little bit more precise here. So let's do exp of theta A, where A was defined using unit length vector. So what do you think the result would be? I'm not gonna do that because it would take a while, but I will at least tell you what the solution is.
3D rotation. 3D rotation matrix?
Yes, exactly. It's exactly a 3D rotation matrix. There actually is a specific formula for it. You can derive it some work. I'm not gonna do that. The formula, it looks like this: sine theta A plus 1 minus cosine theta A squared. And this is always a rotation matrix, so element of SO3. This formula is called the Rodriguez formula. And it's a useful thing. If you have an axis of rotation and an angle, this is how you can compute the corresponding rotation matrix. And if you would have to get exactly the same result by the ODE machinery. If you computed the eigenvectors and eigenvalues of this matrix, and you figure out that's basically how this Rodriguez formula can be derived too. So on a higher level, this was just for 2D and 3D examples. This of course generalizes. So if you want to know what does it generalize to, we discussed about Lie groups, right? Remember? And we had Lie groups. And in Lie groups, we had like rotations, like SO3 was an example of of a Lie group, okay? All rotation matrices. So there is also a thing called Lie algebras. And in the case of rotations, the Lie algebras are exactly these anti-symmetric matrices, okay? So in this case, it would be denoted like lowercase SO3, and that means nothing but 3 by 3 anti-symmetric matrices, okay? And there is a mapping between Lie algebras and Lie groups. The exponential of a matrix maps from a Lie algebra to a Lie group. And the other way around, as you can probably guess, there is a matrix logarithm mapping, which goes from a Lie group to Lie algebra. So if somebody gave you a rotation matrix and you wanted to extract the axis of rotation and the angle of rotation, one way you can do it is by computing the matrix logarithm. The matrix logarithm is just the inverse operation to the matrix exponential. Computing it, it's not always simple, especially for more general matrices. So this generalizes from rotation, this generalizes to many different groups. Not just rotation groups. We had this elementary group. Oh, did I mention what is Lie? What means we had a group theory, right? But we didn't explain what is a Lie group. That just the Lie thing. That was a guy, Sophus Lie, who sort of discovered this thing. And what it means, it's a group which is also a smooth manifold. Okay. So it also has some nice geometric interpretation. Okay, I guess I should probably stop at this point before I confuse you unnecessarily. This is already a little bit beyond the scope, I guess, of linear algebra. This is something I wanted to add. Okay. Is that clear? So we will move on to another, and I guess for now, at least, final example of eigenvalues and eigenvectors, still related to linear differential equations. So this is important for you because it's also related to the next project you will do, starting tomorrow. And that's basically a very simple physics-based system. Spring mass Dasphot system, also known as damped harmonic oscillator. Okay. So the model here is it's a very, very basic physics-based model. If you had some physics class, then you might have already had this. But this will lead us to, so what I'm going to show you is how to solve this using eigenvalues and eigenvectors. And then for the project, we will do like a system of few mass spring elements. So the physics model is really simple here. I guess as simple as it gets. So we are in 1D. Just draw it here. Okay. I have an origin. So we are really, it's a 1D simulation. It's like 1D is like, rarely you have the luxury of working in 1D, but this is the case. And the 1D space has some origin, okay. And I'm assuming there is a mass point which is attached by a spring to the origin, and the spring has 0 rest length, okay? So the spring would be most happy if my mass point, so this is my mass point, the spring would be relaxed if the mass point was exactly at the origin, okay? Well, I'm not going to put it to the origin. I will put the mass point somewhere, right? So if the mass point is somewhere, then the spring exerts some force, restorative force that wants to pull it back to the rest state. And what's going to happen, then the mass point is going to oscillate around it. Now, we will make it a little bit more interesting. And we will assume that there is some environment resistance, that there is this Dasphot element, some sort of damping element, which means that there is this entire system lives in some environment which resists velocities, okay, resists high velocities. So let's take a look how we need some parameters here. So let's go through the slide a little bit. What this will actually go to, because we will be using the Newton's equations of motion, so this results in a second order differential equation. There's nothing to be scared of, because we can just fairly easily decompose it into a system of two first order differential equations, okay? So we'll assume the spring has constant K, so the K is the spring stiffness, okay? Spring stiffness constant. The K is a positive constant. And if it's high, it means that the spring is very stiff, like a steel coil, like muffler in a car or something like that. If the K is small, but still positive, then it means something mushy, like some like rubbery or like very, very elastic spring, okay? And then I can use the Newton's second law of motion, your favorite F equals ma, right? Everybody knows that, where m is the mass of my mass point, so that's some constant, right? If the mass point is heavy, I have high m. M is also, of course, non-negative. And a is the acceleration, right? So acceleration, as you know, is the second time derivative of position. So here I'm in 1D, so here everything is beautiful. Here I have just like a 1D function of positions, right? So this is my just x-axis, there's no y-axis. And this xt is a function, so I guess function that goes from 0 to infinity to real numbers and tells me the position there. If I differentiate it once, I'm getting velocity of the mass point. If I differentiate twice, I'm getting acceleration. Okay? And the Newton's second law of motion says that the mass times acceleration equals the applied forces. Okay? So here I sort of reversed it. So on the left, I have mass times acceleration. Oh, if you haven't seen this dot before, that's what often used in physics to denote time differentiation, okay? So this x dot means just differentiate x with respect to time, and two dots means differentiate twice, okay? I think this is used mostly in physics, this notation. And then what are my forces acting on my mass point? Well, the first one is the spring force, okay? So I said that the stiffness is K, so this force is linearly proportional to the stiffness. So the higher stiffness, the higher the force, okay? Like if a steel spring is stretched to this length, then it will be resisting, then it will be pushing with much stronger force than a mushy spring. And it's pushing in the opposite direction, okay? So if x has positive value, then the force goes in the negative direction because it's pushing it back to the rest state. And the c is the damping parameter, where x prime is the velocity. So the c tells me how the environment the system lives in, how much it resists velocity, okay? So like, imagine this is in air, right? So there would be some air drag resisting the velocity. So that would probably have relatively low c, right? The c, of course, also like a positive constant. Could be 0 if they are, I guess, let's say non-negative. I guess this could also be like this. In that case, there would be no spring and nothing would be moving. So if the c would be 0, that would be like vacuum, that there is nothing resisting the motion. And if the c would be high, that means it's immersed in some like highly resistant environment. Like imagine it's immersed in honey and has to like push its way through it, okay? And the motion of this system is completely characterized by the second order differential equation. Because we need to take, oh yeah, sorry, let's explain here, I forgot. Because it involves the second derivative of x, okay? So this is known, the damped harmonic, this is known as damped harmonic oscillator. Have you seen this? Did you have it in some physics class or something? And have you seen the solution using eigenvalues and eigenvectors? That's what we are gonna do here. Because the nice thing about it, this will generalize to also more complex systems. So the first trick, which is very frequently used when you deal with higher order differential equations, the thing is that the higher order basically doesn't matter, because we already know how to deal with systems of linear differential equations, and there is this very simple trick to convert a higher order differential equation to a system of first order differential equations, okay? So this is what we had on the previous slide. We had the mx second derivative minus kx minus c x prime. So I just divide that by m, okay? So I will get x equals minus k over m, x minus c over m, x dot. So that's exactly what I have here. And then I just add this like dumb equation saying that velocity equals velocity. So this equation like is saying nothing, right? But the point is that this allows me to write this in matrix form, okay? So look at this. I define a state vector as x prime and x, okay? So my state vector, sometimes it's called like phase space or something like that, is the current position of my particle and the current velocity, okay? So it's a 2D vector which contains all the kinematic information. And now I can write this system like this. I can say that the time derivative of my state vector equals this matrix times the state vector, okay? So where this matrix came from? Well, that's exactly, so the first row corresponds exactly to the first equation, right? If I differentiate this, here I will get x twice differentiated, here I get x once differentiated. So here indeed the second row tells me exactly that x dot equals x dot, which is trivial. But here it actually has the non-trivial effect that it couples the individual components here. Okay? Or that's the way how we convert a second order differential equation to a system of two first order ones. Okay? Because here we are taking just one differentiation, here we differentiate just once in time, and the trick is that we sort of tie them together. Okay, so if I write this state simply as y, like as a vector, this is of course a vector, right? So then you can see we are back to the case I started discussing in the beginning of the lecture, which is just a 2x2 system of differential equations. Okay, so again, here we have a function y. Y is a function from, in this case, I guess from 0 to infinity, right? Going to r, because I have to start it somewhere. I have to start at y0, and the time usually does not go negative unless you travel back in time. And we can get a solution by solving this using the standard recipe we have already used once today. So let's take a look at that. Everything is clear here? Yeah? So how do I get the solution? Well, again, the key is to compute the matrix exponential of this matrix A, right? So in this case, you know what? Let me copy the matrix A from the previous slide. So the matrix A was minus C divided by M, minus K divided by M, 1 and 0, okay? So I need to compute the exponential of A times T, where T is time here. And the key to do that is to first compute the eigendecomposition of A, okay? So let's do that quickly. That's actually quite simple. So I need to take the characteristic polynomial, right? So I do minus C over M minus lambda, minus K divided by M, 1, and here is just minus lambda. This characteristic polynomial is actually sort of nice. The minuses nicely cancel. So here I get lambda plus C over M plus K over M. That's nice. So that's just lambda squared plus C over M lambda plus K over M. Okay, so a round of space, but the same polynomial is written here. Okay, that's the characteristic polynomial of this particular matrix, which characterizes the damped harmonic oscillator. Okay, and then I need to find eigenvalues. So it's again just a quadratic polynomial. So I apply the well-known formula. I guess I first multiply it by m, right? To make this a little bit easier. So plus c lambda plus k equals 0. And here I put minus b plus, so the discriminant is c squared minus 4km. That's correct, and divided by 2a. So this is a, b, c. And those are the two eigenvalues, okay? So we have now three possibilities which have interesting physical interpretation. So the question is if the eigenvalues are going to be real or complex, okay? So if the discriminant is negative, then it means the lambdas will be complex, right? So what situation is this, right? So that means that under the square root I have a negative number, so some complex numbers will pop out, right? So what does this mean when it will be a negative? Well, I can also write this as c squared is below 4, is less than 4 km, okay? So you can say, aha, so this is the case when the resistance of the environment is small, okay? Like, so if the c is comparatively smaller than k times m, this is going to be the case, okay? And what do you think is going to be the solution in that case? Or I guess better question is, what do the complex eigenvalues and eigenvectors essentially mean for the solution? That's sort of why I started with the first example, that the complex eigenvalues and eigenvectors, they essentially lead to some oscillations or rotations, okay? So this case means that this will oscillate. So I guess intuitively, right, if the resistance of the environment is small, then it means that, well, maybe it will be damped a little bit, so the amplitudes will be going down, but the system will keep bouncing from one side to another, right? Where was my, here. I guess I can animate it. Here the mass point will be bouncing, bum, 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 bum. Will be maybe, the amplitude will be lowering and will be converging to the origin, and eventually it will get there. But it will take an infinite amount of time. So another interesting case, if this is positive, then I will have a real eigenvalue. I will have actually two different and real eigenvalues, right? And the other corner case when this is exactly the same, okay? So what this means is that means that C is comparatively much bigger than K times M, okay? So what does that mean? Well, that means that the environment really resists the motion a lot, okay? So imagine that this mass point attached using a spring to the origin is like moving in honey or some sort of like, or snow or some environment that really resists the motion a lot. There's like a lot of friction going on. So in that case, the solution looks something like this. So it goes really reluctantly to the rest state, and it does not oscillate, okay? So that's what the real eigenvalues essentially mean. There will be no bounces up and down, right? So I guess intuitively the complex eigenvalues means that there will be some complex eigenvectors, and the complex eigenvectors, or even the complex eigenvalues, they mean there will be some exponential, some e to it, which means cosines and sines, right? So cosine of t, what am I writing? Plus I. Sine t, okay? And these cosines and sines are exactly these oscillations there. In the real case, there's no such thing, so it will just go slowly to the rest state. It will never, how do you call this? It will never go to the other side. It will just move like this. It will never overshoot and go back. In the interesting corner case, I guess, if when this is exactly equal, in that case, we have two eigenvalues which are exactly the same, okay? And this is called a critically damped system. And what that means is that in that case, the system goes as quickly as possible to the rest state without overshooting. So no oscillations, but it gets to the rest state as quickly as possible. That's the critical damping. What happens if the C is 0, by the way? Can you tell me what happens if the C will be 0? The resistance of the environment is none. It will oscillate forever, right? So these amplitudes, they will not be attenuating. They will be just perfect sine or cosine curves. If we're bouncing indefinitely, yes. So I guess the summary of this is that the eigenvalues and eigenvectors are incredibly useful because they essentially help us understand many effects in nature, like vibrations here. It's one way how we can do that. So let me also say that generalization to even higher order, he did second order ODEs, right? If you want to go order 5 or something, that's absolutely no problem. Because we can just apply the same trick multiple times, okay? So basically you take the higher derivatives, you stack them in a vector, and you convert it to a system of first order linear differential equations, okay? And this coupling simply says that if you differentiate once, you get another derivative. So those are linear constraints. You just add them as rows to the matrix, and then the eigenvalues and eigenvectors, they do the magic, and from this matrix, correctly compute the solution of the higher order differential equation. Typically, you deal with just second order differential equations because that's what Newton's laws of motion tell us. But sometimes, on some occasions, you need to go to higher order. Like for example, if you need higher order smoothness in computer graphics, then sometimes you need to go to higher order. Okay, and finally, this is what's going to be your next project. I think I will post it tomorrow. I think you still need to finish your first one, right? But no harm discussing it already now. So basically, that's the idea, doing like a little more interesting example of the damped harmonic oscillator, and doing it this time in like, I would say like 1.5D. Can you read that? Is it too small?
No, we just did this.
You did this?
We had to do something like this.
Oh, really? In what class? Huh.
It was just like a steady state.
Okay. This will be actually the dynamic case. You will take a stretchy spring, you will pluck it, and then you will let it oscillate. Okay, if you already have something like that, good for you. Okay, so this is like I guess like 1.5D generalization of the damped harmonic oscillator. Okay, so what we are gonna do here is a system that, where would I draw that? So maybe I can just draw it here, right? So I assume that these two corner ones are fixed; they are attached to the wall or something. Okay, let's call them like y0. This would be y0, and this would be y and plus 1, and all of these particles are allowed to move only in the y-axis, okay, only in the vertical direction. So they cannot go left and right, they cannot move horizontal, they can only move vertically. So that's why I only need 1 degree of freedom to represent the state of the system. So the y0 and y and plus 1, they're gonna be frozen to 0. I just pin it there, okay. And I will give this some simple elasticity model. I will again say that these are springs that sort of push it back to the rest pose. The rest pose would be that this entire system is exactly flat. Okay, so the idea is if I stretch the springs, they resist the stretching. They want to go back to the rest pose, right? But now I have dynamics explained by Newton's second law of motion, and I also have some resistance of the environment. So if I pull on the spring and then I release it, then it's gonna vibrate in an interesting way. Okay, and that's what you will be simulating. And it turns out that in this case, it's just a relatively simple generalization of the damped harmonic oscillator. Okay, so let's figure out what are the forces acting on everything. So the degrees of freedom will be, this would be like the y1, y2, and so on, right? So in general, if I have like a node yi, and it had some neighbors, for example, here's yi minus 1, and here would be yi plus 1. Then the forces acting on the node y, so this is again Newton's second law of motion, okay? So this is mass times acceleration equals the forces. And I'm explaining what the forces are. So the model of the forces, I think we had this at some point, is basically just take the linearized stretch of the spring. Okay, so I simply subtract yi minus 1 times iy. So due to this spring, I will have a force k times yi minus 1 minus iy. Okay, so the point is if aiy minus 1 is below yi, that means that this will be something negative and the force will be pulling this thing down back to the rest state, okay? And we're pulling it, the more the spring is stretched, okay? If I was like higher up, the force would be stronger, and the case, again, the spring stiffness, okay? So the springs are strong, they are pulling it stronger down, or back to the rest pose to be more accurate. This is the same thing. This is the force from the second spring will be just K times yi plus 1 minus yi, right? So that's what you have here. And here is the damping term. So this is just the resistance of the environment with the constant C. The C would be the damping coefficient. So if C is 0, there is none. If C is high, it's immersed in some sort of thick environment which resists motion a lot, okay? So in this system, and again, we do the same trick. We just convert it to a system of first order differential equations, okay? And what do we get is a matrix like this. So here the y would be the state of all the non-constrained degrees of freedom, okay? So the y in this case would be my y1, y2 up to y, and my actually n, okay? I said that the number n plus 1 is constrained and y0 is also constrained. I still need to account, of course, for these springs, okay? If I'm looking at yn, then this spring is still pulling that down, okay? So this is the state, and I also append to the state the velocity. That's the y dot, right? So that means that means the velocities of the individual particles. And if you write down these formulas in matrix notation, plus the coupling that the derivative of y equals the derivative of y, that just gives you an identity matrix. And this is basically just writing these formulas. So these are the damping terms here, and this T is essentially a Laplacian matrix which has this kernel. So that's exactly this stencil here. We have seen this before, the Laplacian stencil, and you will probably see it more and more. So that's just summing these two force terms together, okay? yi minus 1 minus twice yi, because it's here and here. We assume that all the spring constants k are the same for all the springs, so we can just put it together and we get this simple stencil here. Okay, so what you get here is a system of linear differential equations. This time is bigger, right? What's the size of this matrix? What's the dimension of this entire matrix? Well, obviously it's 2n by 2n, right? Because my state vector, this entire state vector, y dot and y, that would be a 2n dimensional vector, because I have all the degrees of freedom of all the particles in there, okay? And the beauty of this system is that here you have the luxury of writing down an analytical solution. That rarely happens to you in practice. That's because this is just a simple linear model. I mean, rarely, depends on what you do. I'm more talking like about computer graphics applications where you have to deal with large rotations and so on. So there would rarely happen to you. But here we have the luxury of analytical solutions. So you just do the standard thing we were talking about today all the time. So you just compute the exponential of this matrix. You give it some initial state. So the good initial state would be, I have the project here. The good initial state would be like this, okay? So you pluck it at the middle particle, you pull it up, and then you say, hey, this is my initial state. So that means you release it from there, okay? And what would you expect? Well, this thing would go back and would oscillate, right? Depending on what parameters you set. If you set this, then you can experiment with the parameters and see what it does to the simulation. The beauty here is that you don't have to worry about any numerical integration, because you just have a perfect solution for the motion. That's a luxury which you typically don't have in physics-based simulation. And that's a luxury because we are assuming such a simple 1D model here. Already, if you go to a mass spring system model in 2D or 3D, then the system of differential equations would not be linear, and writing down an analytical expression is probably impossible. So in that case, you need to switch to discrete solution methods for differential equations, which opens up an entire can of worms, which we then study in phys-based animations. Yeah, it's 563, like explicit Euler, implicit Euler, and all things can go wrong. So the nice thing here is that they don't. If you do the exponential right, you just get a perfect solution you can display that. Okay, so yeah, so this is the project. I think I will take another look at it and post it tomorrow, as usual. And that's all I got to say to you today. Do you have any questions? Okay, I think this should be a fun project to do. All right, okay, thank you, Ben.